Okay, we're continuing here, still chapter 14. Almost to do the first part. All right, so last time we got into salts and hydrolysis. And remember, really, salts are formed from a reaction, right, of our acid and base, is essentially where they come from. Gives us basically a salt plus some water. And it really is important, sort of, where that salt came from, or part of that salt came from, in terms of whether or not it'll go through hydrolysis. Hydrolysis basically is a reaction with water and that salt. And as we saw there, in some cases, the salt will accept an H plus there from the water. The result of that is obviously look at our salt plus an H plus, and we will produce hydroxide. And that would then make that solution basic, as we talked about. We also could have a situation where the salt will actually sort of send the H plus over. And the result of that is our salt here will be less than H plus, minus an H plus. And we will end up with H3O plus, which means it will be an acidic solution as well. Now, again, what salts will go through hydrolysis or not go through hydrolysis, again, depends really where they came from. So remember, it's basically that opposite relationship. So if you have something that came from either a weak acid, like this situation, uh, it will produce a conjugate base that will go through hydrolysis. And again, it will do pretty much what we see up there, produce hydroxide. If you have something that comes from a weak base, like that situation, it will then have a conjugate acid that will go through hydrolysis. So basically, anything that comes from a sort of a weak acid or weak base, the salt that's produced from that will have the ability to continue to react with water through this hydrolysis process. And the result of that is it's going to basically introduce into the solution more H plus or more OH minus, which is going to make it either acidic or basic. There are neutral salts, as we also talked about. Neutral salts essentially come from strong acids are really strong bases. So remember, anything from kind of group 1 and 2, except for beryllium, are pretty much neutral. Um, and again, that's really because that's where we find a lot of our strong bases really come from. And also anything that comes from a strong acid, like we saw chloride a couple of times there. And again, chloride coming from hydrochloric acid is going to be relatively weak. So these guys are neutral salts, which means you would expect a pH of about 7 if you just have a salt solution of those guys. Obviously, as we also did, it can involve obviously calculations. If you have a salt that's going through hydrolysis, it does require you to do an ice table. And as we saw in some of those examples and talked about, there are usually cases where you're given the wrong K value. So again, that Ka is times Kb is equal Kw. It's also something that's very commonly used in sort of hydrolysis problems to convert it to the right K value. So that's a super common mistake people make, is they use the wrong K value when they're going to do these type of calculations. Any questions on that stuff there? All right, then continuing on here, part 1 of chapter 14. Talk a little bit about oxides. Oxides are obviously substances or elements that have oxygen attached to them. And some are acidic oxides, some are basic oxides. Over here, we see a lot of our basic oxides. So, you got a little sodium oxide plus some water. That's going to eventually probably get you down to some sodium hydroxide, right? So again, a lot of our sort of strong bases coming from group 1 and group 2 on the periodic table, as we talked about. Over here in our non-metal region is where a lot of our acidic sort of guys come from. So for example, we got a little CO2 plus some water, gonna make some, not what I was gonna write there, H2CO3, a little carbonic acid, also nitric acid coming from this guy here as well. So a lot of those guys over there are kind of non-metal. Non-metals, guys that have oxygen, will kind of produce with water acids. And then there are some that are amphoteric, like our beryllium, and also a couple of these guys down this way are amphoteric, which again means the same thing as what we talked about earlier. Could go either way. Could be an acid or a base, depending on the situation. Um, we also talked about last time as well, speaking of sort of salts and that type of stuff. Again, if it is possible, again, that both parts of the salt can go through hydrolysis. And again, in that case, we do compare the Ka to Kb value to see which one is larger. Now, we've talked about a couple of different definitions of an acid and a base. We have the Arrhenius definition, which basically just means that it produces sort of H plus or H3O plus in solution. We also have our Bronsted-Lowry definition of an acid, which is a proton donor. So a third definition of an acid comes from our friend Lewis, and a Lewis acid, when we think about Lewis, we think about Lewis structures, right? And Lewis structures involve electrons. So it may not be a surprise that a Lewis acid is a substance that will actually accept a pair of electrons. So a Lewis acid, and you could also have, as we will see in a number of chapters sort of coming up, a Lewis base, and that's something that will donate a pair of electrons. So this is a more sort of generic definition of an acid and base. It's dealt with a lot in transition metal chemistry, also a little bit in organic chemistry, and sort of how things sort of happen. But here we're talking about electrons and not protons. So it is opposite for Lewis acid and bases in terms of who's accepting, who's donating. And again, we're talking in one case about a proton in the Bronsted-Lowry definition. We're talking about H pluses here, and we're talking about electron pairs here. Now, in order to kind of donate an electron pair, you need to have some non-bonding electrons, and like a polar situation is pretty much good, or things that are negatively charged are typically really good Lewis bases because they have extra electrons to donate because they are negatively charged. Things that are good Lewis acids are things that are technically deficient in electrons. Thank you. Things, for example, like incomplete octets, like boron, which has less than 8 electrons, so it's got room to sort of accept those things. Also, things with positive charges, right, it means that they have lost electrons, so they're electron deficient, so they have a place to accept those electrons. So if we take a look at this situation here, which is our H plus and our OH minus, in this particular case, this is OH minus, it can donate some electrons over, and that's going to make it the base, the Lewis base. And this, it will accept the electrons, which is the Lewis acid. Again, it's positively charged, which means obviously it's missing some electrons. So that works really well. Here in this situation here, this is ammonia, which is again not negatively charged, but it is polar and has those non-bonding electrons on the nitrogen, which allows it to donate its electrons over and again become a Lewis base. And here is our Lewis acid, right? So that's sort of our Lewis acid base definition. Does it give you a different outcome than, say, Bronsted-Lowry? In this case, it doesn't, and it shouldn't if you have an H plus involved. If we looked at this more as the Bronsted-Lowry definition, this guy is going this way, right? So he's donating an H plus, which would make him a Bronsted acid, and the OH minus is accepting the H plus, which would make it a Bronsted base. So regardless of the definition you take, the OH minus in both cases are the base, and the H plus in both cases are the acid. Same thing here in the Bronsted-Lowry definition, you know, kind of think about it that way, even though maybe not how it truly happens, but the H plus is kind of coming over there to the NH3. And once again, he's donating an H plus, which would make him the acid, and the NH3 here would be accepting the H plus, which would make him the base. So again, you can see you get the same results regardless of sort of which one you look at. So if there is an H plus involved, you can just look at it as Bronsted-Lowry, and you can still figure out, you know, obviously who's the acid or base. The benefit, though, of something like a Lewis acid base sort of situation is a situation like this where you actually don't have any H pluses being transferred. So in this case, we have no H pluses being transferred. And in this case, it's going to be these electrons heading over to our incomplete octet, our boron, which is electron deficient. And they're going to bind here. And again, no H pluses being transferred. But again, this is going to be our Lewis base because it's donating those pair of electrons. and this would be our Lewis acid. So what this allows you to do is sort of apply an acid-base sort of context to something where there is no proton being transferred or accepted. And you look at the electrons being accepted and donated. Again, we will see this a little bit more when we get to transition metals and complex ions. It's sort of this situation. And you may see it when we go to organic a little bit, is sort of how some of those interactions sort of occur in a more Lewis acid, Lewis base situation. Any questions out there? All right, the last thing we're going to talk about is polyprotic acids and sort of how polyprotic acids work here. And polyprotic acids are acids that have more than one H plus to give. So we have basically something like this, which is monoprotic, right? Basically has one hydrogen to give if that's an acid. H2A is diprotic. Again, it's got two hydrogens to give. And H3A here is triprotic. Our polyprotic has three hydrogens to give. So when these hydrogens come off, as we might have touched upon earlier on in the chapter, they do come off basically one at a time, so they don't all just drop off at once. So for example, if we take phosphoric acid here, which is H3PO4. So the first thing that will happen is basically the H3PO4 will drop off one hydrogen, right, and create H2PO4 minus. And to do this, this is going to give us a Ka1 value, and that's basically the equilibrium constant for the first hydrogen coming off in this situation, which according to this looks like it's 7.5 times 10 to the minus 3. The next thing that will happen is that guy that has already basically lost one H plus will then go ahead and drop its second H plus here. And we will be left with HPO4 2 minus. And there's also an equilibrium constant for this step, which is known as the Ka2 for the second hydrogen basically coming off. And there we see it is getting a little 6.2 to the minus 8. There it is. 6.2 times 10 to the minus 8. And lastly, this guy that's already lost a couple of hydrogens there will go ahead and drop its last hydrogen in this case, and we will get our phosphate here. And that will be our Ka3 value, minus 13, I think. Yeah, 4.8, so minus 13. And this again comes off one at a time, as we talked about. It's what maintains our Bronsted-Lowry acid conjugate base pairs, right? So this guy and this guy is a pair. Again, the only difference is one H plus. This guy and this guy is a pair, right? So it's only one H plus. And this guy and this guy is a pair, which is only one H plus. Again, why H3PO4 minus, or H3PO4 and PO4 3 minus are not acid conjugate base pairs. Now, sometimes in like a previous class, you don't really look at the stepwise sort of dissociation of it. You see the overall reaction, right? And for example, if we added all these together, that would cancel, this would cancel, and you're left with probably what you wrote in the previous class if you had something like this: 1, 2, 3 H pluses and phosphate, right? So that is sort of the overall reaction that's happening when all the H pluses come off, but they do come off in a stepwise fashion. Is it easier to remove the first one or the last H plus? Which one's easier? It is definitely easier to remove the first H plus, yeah. First H plus that comes off, right? Thing's neutral, so it drops it off, not too bad. Once you do that, you now have kind of a negative charge, and now you want to rip off something that's positive, so that makes it a little bit harder to do. And once you rip off maybe that second one, you now have something that has a -2 charge, which is going to make it even harder, right, to remove something that's positively charged. And we see that actually with our Ka values. If we look at the comparison of our Ka value for the first hydrogen to the second to the third, the Ka value gets smaller as you go remove one hydrogen after the other. And when it gets smaller, right, and we have a smaller K value, that means that we mainly have reactants. So when we get down to here, we're mainly keeping this guy. Not very much of that guy's going to come off at all. And a lot less of this guy's going to come off than it did here at the very beginning, as there's a fairly big difference in value or magnitude between the Ka1 and the Ka2 value here. So it does get progressively harder to remove those hydrogens, and you see that with each of these different sort of polyprotic acids. You can see we go from -3 to -8, -7 to -11. Earlier, we talked about that strong acids typically do not have Ka values, and as I mentioned before, probably the only one maybe you might see on a table like this is sulfuric acid. And as you can see on this particular table, it just says very large for the first one, which is not super helpful. But it's on the table because once that first hydrogen comes off, what you're left with is definitely a weak acid that does have a Ka value. So um, if we wanted to do sort of a calculation involving something like phosphoric acid, and we wanted to figure out sort of the pH of that solution, it is a little bit of a different sort of calculation that we might have to do. Not super different. We'll come back to that, I think. So why don't we take a look at a problem like this, and let's just say we wanted to figure out everybody's concentration here, basically the phosphoric acid and pretty much all the sort of intermediates along the way as each of those hydrogens come off. And we also want to figure out the H plus concentration of a 5 molar phosphoric acid solution. So here are 3 K values, or Ka1 for the first hydrogen that comes off, our Ka2 for the second one, and our Ka3 here for our third hydrogen that comes off. And if we wanted to basically figure out everything that's going on, we would start with really our first hydrogen. So we'll do that here, I think, maybe. But let me change the page. There we go. So we'll go, our very first thing that's going to happen is our H3PO4 is again going to lose that first hydrogen. And again, we'll be left with H2PO4 minus. And as we saw there, the Ka1 is 7.5 to the -3. So if we are starting with 5 molar phosphoric acid, we can do an ice table here like normal. So we'll go zeros and zeros. The change here will be -x plus x plus x. At equilibrium, we got 5 minus x, x, and x. So a regular normal table here. This would go into our Ka1 expression, which again is just like any other equilibrium, our products divided by our reactants. And in this case, our Ka1 value is 7.5 times 10 to the -3. Putting in our values here to solve for x gives us x squared divided by 5 minus x is going to equal 7.5 times 10 to the -3. I'm going to make an assumption here and assume x is equal to 0. And that's going to give me x squared divided by 5 is equal to 7.5 times 10 to the -3. We're going to multiply that to the other side and square root it. And we will end up with a little square root action. We'll end up with an x value here of 0.194. We do need to check it to make sure it's all good. So we'll take that, we'll divide it by 5 and times it by 100 just to check it. And it's going to be good because I did change the concentration to make sure it didn't feel quadratic-y today. So that is 3.9% here. If you did it with 1 molar phosphoric acid, you would probably have to quadratic it. So that check is good. Thank goodness. And what that means is from the very first sort of dissociation of the hydrogen that's coming off, we do have a few answers. We have in this case our concentration of H plus will equal 0.194 molar. Our concentration of H2PO4 minus from this table is 0.194 molar. And our concentration of our phosphoric acid would be 5 minus 0.194, and that's going to get us here. Yeah, we'll call it 4.81 molar. So off of this very first ice table, we actually just knocked out 3 of what we were looking for pretty much on our question. So if we kind of go back there and take a looky here, maybe. But let me go back. So there we go. So we just took care of this, this, and this off of the first table. We do need to actually continue on with our dissociation because we got to get to this guy here and figure out what its concentration is. So that's going to require us to go to the second hydrogen that will come off, which goes with our second Ka value there. So let's take a look at that there. So the next thing that's going to come off, as we talked about, is that guy that has lost 1 hydrogen will then lose another hydrogen. And we will end up with something like this. And again, we're kind of looking for this guy in this case. And this would be our Ka2 value because it's the second hydrogen that came off, which was 6.2 times 10 to the minus 8. Now, initially here, we already have some of these guys floating around. So we take a peek there at our previous slide here. We have this guy, which is X, still in the solution. And that means that that is 0.194. Now, what about H plus? Do we have some H plus in there already? We do, right? Because it came off the first time as well. So we have our equilibrium amount of H plus in the solution as well. And that's going to give us 0.194. So we're sort of using our equilibrium concentrations from the first hydrogen that comes off as our initial concentrations for the second hydrogen that's going to come off in our ice table. Any questions on that there? The rest of the table here is going to be the same. It's going to be minus X, plus X, and plus X. That means maybe, there you go. When we reach equilibrium, we got 0.194 minus X, 0.194 plus X, and X. This now can go into our Ka2 expression here. And our Ka2 expression, again, would be our products divided by our reactants. So put it in our numbers there, will give us 0.194 plus X times X divided by 0.194 minus X equals 6.2 times 10 to the minus 8. Why not make our assumption here that X is equal to 0? Again, we're going to get rid of basically this X and this X here. We're going to 0 out. Got to keep 1X. We got nothing to solve for. So 0.194 times X divided by 0.194 is equal to 6.2 times 10 to the minus 8. I feel like I could do that maybe without the calculator. Those are going to cancel. And that's going to give us an X value in this case of 6.2 times 10 to the minus 8. We do need to check it, so we can divide it by 0.194 times it by 100%. And I think the check should be good. Don't even think you're at 1% at all. So you're way less, so it's good. All right, so what does this give us? If we go to this ice table, we could clearly see that the concentration of HPO42 minus, which is one of the things we were looking for, is going to be equal to X, which means it is 6.2 times 10 to the minus 8 molar. Now, when I put this X value that I just got here, when I take this X value and I put it back in for H plus concentration, what happens to the concentration of H plus? If you take 0.194 and you add it to 6.2 times 10 to the minus 8, you end up with still 0.194 basically. Yeah. And same thing here. If I take 0.194 and I subtract it from 6.2 times 10 to the minus 8, you basically still end up with the same number. So it did change, but not enough to overall change the concentration. Any questions on that there? All right, so by doing this one here, we have now taken care of this guy. That leaves us really just phosphate that's left, and phosphate can only be found if you remember sort of those equations we did on the previous slide in the very last step there where the last hydrogen comes off. So that will require us to basically get all the way down to the last hydrogen here. And let's take a look at what that will be looking like here. So we'll take our very last hydrogen is going to come off. And that means we've already lost a couple here. And it will drop the last hydrogen. And that's where we're going to find our phosphate, which is what we're looking for. And again, that's going to be our Ka3 for our third hydrogen, 4.8 to the minus 13. Once again, just like we had in the previous table, we do have an initial amount of our HPO42 minus, and that is coming right here. So again, we're going to use our equilibrium concentration we got on the previous step as our initial concentration. So that would be this number here, the 6.2 times 10 to the minus 8. So here we go, 6.2 times 10 to the minus 8. Now, in terms of the hydrogen, I also still have hydrogen there in that solution. And as we just talked about, basically it's still going to be 0.194 because when we add that X to it on the previous step, didn't really change the concentration. It's still hanging out at 0.194, and this would be 0. So again, we got a few things in that initial sort of step. Minus X for our change, plus X, meaning at equilibrium, 6.2 times 10 to the minus 8 minus X, 0.194. By the way, that is plus X and X. This again, just like in the previous steps, will go into our equilibrium expression, which is our Ka3 expression. And that's again going to be our products for our reactants. And that's going to equal 4.8 times 10 to the minus 13. Putting our numbers in, 0.194 plus X times X divided by 6.2 times 10 to the minus 8 minus X equals 4.8 times 10 to the minus 13. We've been doing good on the assumptions, so why not go for the trifecta here and hit the third one. X is equal to 0. Once again, it's going to be our pluses and minus that we're going to get rid of. That's going to reduce this down to 0.194 times X divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the minus 13. We're going to multiply that guy and then come back and divide that guy afterwards. And that's going to get me divided by 0.194. It's going to get me like a 1.5 for the X value here, 1.5 times 10 to the minus 19. Again, we need to check it, so you can pick either one. So you could divide it by 0.194 and times it by 100. And I think you should still be fairly safe, and you are. You're nowhere even near 0.1%. So again, the check here is good. That again is what's going to allow us now to get to our phosphate concentration. As you can see from our table, in this case, X equals the phosphate concentration. So what we got going on at this point is, we got there 1.5 times 10 to the minus 19 molar in this case. And once again, if we take this X value at this point and put it back into here, it's pretty much going to stay at 0.194. If you add, 1.5 times 10 to the minus 9, it's not going to really change. Nor is it going to really change when you put it back into here. It's going to basically stay at the same concentration. And that again allows us to get all the way to the phosphate in this case, which required us to go all the way to the third sort of step there. Now we got the phosphate. So the only thing we're missing really is the pH. And let's talk about the pH here, which is minus the log of the H plus. When we look at what is going on in this dissociation, the majority of all of the H plus that came off happened in the first step, the second step, or the third step. Where was the majority of the H plus that came out? It was the very first step, right? If you look at the H plus concentration here at the first step, 0.194, right? Basically, if we go to our second step, the H plus concentration that came off was 6.2 times 10 to the minus 8. A lot less came off, right, in that second hydrogen, indicating what we saw with the Ka values, that it gets a lot harder, right, to remove that second hydrogen after the first one comes off. Gets even harder when we get to the third one, because now we're only dropping off 1.5 times 10 to the minus 19. Barely anything, right? It's coming off. Super hard to get that third hydrogen to pop off, basically. So what we see here is the majority of the hydrogen did come off here in the first step, and that is usually the case for polyprotic acids, which means if you had a problem where you were asked what is the pH of a polyprotic acid, like phosphoric acid or sulfuric acid or any of those kind of guys, you probably would be safe in most cases, 99.99% of the time, just to take the H plus from the first step and calculate the pH off of it. And you wouldn't have to worry about the other steps. So if we did that here, our pH would be minus the log of 0.194. That's going to give me a pretty low pH, I think. That's going to get us a 0.71 pH, which definitely is acidic in this case, along the way. Now, again, like I said, if you're just interested in the pH of a polyprotic acid, just do the first ice table, get the H plus concentration, and knock out the pH from that, and you should be in good shape. If you have a problem, obviously, like this one, where you have to figure out everybody's concentration, it will require you perhaps to go to the second step. And again, here we had to go to the third step because that's the only place where we find phosphate. So you had to go all the way to sort of the third hydrogen coming off. Any questions on polyprotic acids and how to deal with those calculations? All right, so as we saw there, acids can furnish more than one protons of polyprotic acid. Um, they do come off, as we've been talking about, in that stepwise fashion. The conjugate base of the first associated step becomes basically the equilibrium of the next step, or the starting point. And as we saw there, again, it gets progressively harder and smaller K values as you keep pulling off those hydrogens. And typically polyprotic acids and water, only the first step is the important one, as we just saw with our example there. Basically, that is where all of your H plus comes off. And again, you can just use that to calculate your pH. Questions on that there? All right. I believe, if I'm not mistaken, that wraps up part 1 of chapter 4. All right, so the bad news of part 1 is there's a part 2 usually. So part 2 here of chapter 14 really is, as we will talk about, as we talked about before, it is the height of the roller coaster hill. Yes, so we're almost to the height of the roller coaster hill. So we're now going to put together a lot of stuff that we've learned in the last couple of chapters. And again, conceptually, you do need to understand sort of what is going on in the rest of this chapter. Again, usually fairly difficult for a lot of people is this section we're going to come into. All right, so let's talk about the first thing, maybe if there's something there. And the first idea is what is known as the common ion effect. And the idea of the common ion effect is an equilibrium. If you have a common ion present, it will suppress basically the dissociation of a weak acid or a weak base. So the idea here is this: if we take a look at, let's take a look at a common example here. I'll come back to a couple pages here, maybe. Yeah. So let's just take acetic acid, for example, which is this. And acetic acid is a weak acid. It's definitely not one of those 6 sort of strong acids. And acetic acid, if you just had acetic acid by itself in solution, is going to set up this equilibrium. And it's going to set up this equilibrium, arrows and all in the beaker. And there's the left side and the right-hand side as well in our beaker. But it's going to break apart into H plus and acetate in this case. So under normal conditions, if you just had acetic acid by itself, you're going to get this sort of setup that's going to happen, and it will dissociate. It will mainly stay together, will produce a little bit of H plus, which is again why it's a weak acid, and it's a reversible reaction. So now if we took acetic acid and we decided to add a little sodium acetate to it, right? And sodium acetate is a salt, right? And because it's a salt and an ionic compound, it is not going to set up an equilibrium. It's basically just going to break apart. So when you toss some sodium acetate in there, this thing is going to break apart into a sodium ion and an acetate ion. So that is basically what is going to go for a swim there when you toss a little sodium acetate into the pool with our acetic acid that's in there. Now, you could probably see that when you do that, because it's going to create both of these ions, basically 100%, the common ion we are talking about now is the acetate ion, right? So essentially, we're adding more sodium to this equilibrium and we're adding more acetate, right? And acetate, if we look at this equilibrium, is right about there. And our good friend Le Chatelier's principle says that when we would add more acetate to this equilibrium, will this cause this equilibrium to shift to the right, to the left? No change. What should happen in this case? It should cause this equilibrium to shift to the left, away from the side we're adding to. So we should see a shift in the equilibrium to the left here, based off of Le Chatelier's principle. Now, what does that affect? That affects a couple of things, especially if we're thinking about the pH here, which is minus the log of the H plus concentration. So when we have this shift that occurs because of the presence of this common ion, does the concentration of H plus in the case up here, does it go up or does it go down, the H plus in this concentration? Should go down, right? So if we shift it to the left, we're going to see the concentration of H plus go down. And when the concentration of H plus goes down, the concentration of OH minus goes up. And when the concentration of OH minus goes up, that means we now have more base, right, in the solution than acid that we started with. And what we will see in terms of the pH in this case is in the presence of the common ion, we will actually see the pH go up, yeah, from just the weak acid by itself. And that is because it is suppressing this guy from releasing those H plus into the solution, which would make it normally more acidic. And because we're getting less H plus, we actually have a higher pH. Does that mean that the pH will be basic in this case? The answer is no. It's just going to be a higher pH than what you would start with acetic acid. So probably won't jump to a basic pH, but instead of maybe like 4.74, maybe you got like a pH of 5 point something, so a little bit higher of a pH than where it started. Any questions on that? So this is the idea of a common ion effect. When you have the presence of those common ions, it's going to always cause the equilibrium to shift to the left. And this works also with weak bases. It's the same idea. If you have a common ion with a weak base, right? If you had something like a weak base, like say ammonia here, which would break something like this. If you added something like, some ammonium nitrate or something, right? And that's going to cause this equilibrium maybe to shift to the left. And when it shifts to the left, the concentration of OH minus in this case will go down, which means the concentration of H plus will go up. And instead of a higher pH that you started with that weak base, you'll also see it drop a little bit and actually become heading towards the acidic side, more acidic than it started with. Again, probably won't become acidic or anything like that, but it will definitely be a lower pH because you now have less OH minus in solution. So that's what it again is meant by a presence of a common ion will basically cause either a weak acid or a weak base basically to stay together. The result of that is you get less H plus in the case of the acid, you get less OH minus in case of the base. And what that has the effect is it affects the pH of where it would be if you didn't have that common ion present. Any questions on that there? So the presence of that common ion, again, as we just saw there, based on Le Chatelier's principle, going to cause that equilibrium to shift to the left and going to keep it together. Again, out of those two things, when you have a common ion, mostly likely coming from a salt, that salt, because it's a strong electrolyte, will not set up an equilibrium. So we really just have the weak acid or the weak base here setting up that equilibrium. and the other one basically almost like you're adding it. So it really is sort of like a Le Chatelier's principle sort of idea that's occurring. So let's take a look at so how this will affect perhaps the pH of a solution. And so let's take a look at one of these here. Why don't you start with A? So in A, we want to calculate the pH of a solution that is 0.2 molar acetic acid. Here is the Ka value for acetic acid. So why don't you just do part A first and see what you come up with. Yeah, let's take a look here. So the first one here, we got 0.2 molar acetic acid. And we got a Ka value there of 1.8 times 10 to the minus 5. So clearly we have a Ka value, so we do know this is a weak acid, and if it's a weak acid, we need to do an ice table, and that's what we will do like we did it earlier on here. So CH3COOH. Again, going to break part into H plus here and acetate. Initially here we have 0.2, 0, and 0. Change would be minus x plus x plus x. That means at equilibrium 0.2 minus x, x, and x in this case. Question on the table. All right, like normal, we're just gonna pop that into our Ka expression, which is our H plus, our acetate, and our acetic acid there. And is equals 1.8 times 10 to the minus 5. That gives us basically x squared divided by 0.2 minus x equals 1.8 times 10 to the minus 5. Doing good on the assumptions today, so why not continue? X is equal to 0 here, we're going to assume. That gets us x squared divided by 0.2 equals 1.8 times 10 to the minus 5. Again, we're going to multiply and then square root afterwards. So we'll get that there, minus 5 times 0.2, a little square rootage. Yeah, it goes 0.001. I don't know. We'll go 90, I guess. In this case, we do want to check it here. So we're going to divide it by 0.2 times it by 100. So we'll divide it by 0.2 times it by 100. And we're at 0.9%. So check is good. That would mean here my H plus concentration is equal to 0. Whatever I have there, 0.00190. And if I put that into, that would be molarity, put that into my pH minus the log 0.00190, gonna get you 2.72 to open up here. Yeah. So our acetic acid solution in this case has a pH of 2.72. So it's good and acidic. Any questions on that there? So that's just a regular sort of Ka problem like we did earlier on in this chapter. So now let's take a look at what is happening in part B and how it's different. So in part B, we're still using the 0.2 molar acetic acid, but we're going to add 0.3 molar sodium acetate to it. So let's take a look at that together here and see what maybe changes. So we got 0.2 molar acetic acid in part B. Little B there. And we're going to add 0.3 molar sodium acetate to it. And obviously here our Ka value is still the same. And it is based off of our weak acid. So in this particular case, when we toss both of those things into our beaker, it is only the acetic acid here, which is our weak acid, that's going to set up the equilibrium. So once again, it is this acetic acid, arrows and all in our beaker, will set up this equilibrium here in there. When we add our sodium acetate, as we talked about earlier, that is a salt, which makes it a strong electrolyte. So it's really not going to set up any type of equilibrium. It's just going to break apart. It's really just a source of those two ions in this case, right? So when we take our sodium acetate, because it's that salt, it's going to do a one-way street here and basically just be a supply of sodium ions and acetate ions. And obviously, in this case, it is the acetate ion, right? That is our common ion that is present. So when we go to do this calculation, we still do it like we did before. And because the weak acid is the only one that sets up the equilibrium, that is where our ice table comes from. It comes from the weak acid, just like we did previously. So we will set up our equilibrium, an ice table type problem, using our weak acid. And initially here of our weak acid, we have 0.2 molar. We have 0 of our H plus. Now, what about our acetate? Do we have any of that here to start with? The answer is yeah, and it's coming from the actual sodium acetate in this case. So this sodium acetate, again, is a source of acetate. And because it is a 1-to-1 relationship between those two things, the concentration of our acetate in this solution is also 0.3 molar. And we would have an initial concentration of 0.3 molar on this side. That is super important when you're doing this ice table, because if I zeroed it out, what would I end up with? The exact same calculation I just did, right? Which is just a weak acid, no common ion present. I would say big error people always make. They're so used to, at this point, just rolling zeros on the right-hand side. When they get to this problem, they just like auto zero out that side. And again, if you do that, you're essentially just repeating the same calculation that we just did a second ago, which is not obviously the correct calculation in this case, since we have that common ion present. The rest of the table here is going to be the same. It's going to be minus x, and plus x. And that means at equilibrium here, 0.2 minus x. Probably the next common mistake that people make is they're so used to doing minus x that they do a minus x here on the right-hand side, but this is plus x. So probably the second thing that's very common that people kind of screw up on, frankly, is doing that. Any questions on the ice table? So that part right there is super important if you're doing an ice table in this type of calculation. Otherwise, you're frankly not doing the right calculation. You're just doing the same calculation over again. We are again going to just go into our Ka expression at this point, just like we did previously. So again, same deal. It's going to be our H plus, our acetate, and our acetic acid. And again, it is still that same Ka value that goes with the acetic acid. So in this case, we will end up with x times 0.3 plus x divided by 0.2 minus x equals 1.8 times 10 to the minus 5. Again, I'm going to assume x is equal to 0 here. And again, that's only going to take out the x's we're adding or subtracting from. So that will get us x times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. A little multiplying, then dividing to the other side. And that will get us here 0.2 times 1.8 to the minus 5 divided by 0.3. Going to give us an x value here of 0.1234. I could have probably used sig fig there, I suppose, or scientific notation. As we got here, we want to divide and check it. You could do it by either one, so I'll just do the 0.3 and times it by 100% just to double check we're good. And we should be. Again, you're at like 0.004%, so the check here is good, yeah. So again, if we go back to our ice table, we can see that X is the H plus concentration. So that means that we can call that the H plus concentration, put a little molarity on the back end of it. And that means our pH in this case minus the log of 0.123412. And that's going to get us here a pH of 4.92 in this case. Any questions on that calculation? Yeah. We're using it because we basically have two things here that we, if you want to think about it. So we basically have, in this example, we basically have two things that we tossed in there, right? We tossed in some acetic acid, which is a weak acid, right? And we tossed in there some sodium acetate, which is really just a salt. And when we do this, because this is a salt, this is a strong electrolyte, which means when it goes for a swim into the pool here, it's not gonna stay together. It's gonna completely break apart. So basically, all that's gonna do is just send in there these ions freely by themselves. It will not set up an equilibrium. Now, when we put our weak acid in, because it's a weak acid and it's a weak electrolyte, it will set up an equilibrium. So out of those two things, it's really just this acetic acid that's going to come into here and basically set up this equilibrium, right? And because of that, and that's the only thing that sets up an equilibrium, that is where the Ka value comes from. That 1.8 times 10 to the minus 5 is the Ka value for this weak acid. And because that's the only thing that's going to set up an equilibrium, that's where we're going to do our calculation from. And that's why we're using that. This is essentially like if you, when you're doing like the Chatelier's principle and you had acetic acid in a beaker, you grab the bottle of sodium acetate and you're just kind of adding these things in. And that's what's happening here. Basically, this guy is adding into this equilibrium because now we have a lot more free kind of acetate in that solution, and that's going to increase the amount of acetate and cause that equilibrium to shift to the left, basically. And again, what we see as a result of this, if we just look at the pH values, right? We talked about because of the shift in equilibrium, the amount of H plus that we have in this situation is actually less than the amount of H plus that we had with just the acetic acid by itself. And we see that in the pH. Acetic acid by itself, which is able to release a lot more H plus than it can in the common ion situation, has a pH of 2.72. So it has more H plus, lower pH than what we see here in the common ion. Because of that equilibrium shift, we actually have less H plus in that solution. Less H plus in that solution raises the pH here, right, from where it started. And we now have a higher pH. Again, not basic, but it is going in the upper direction there from where it started, and we end up with a pH of 4.92. And that is a direct result of having that extra acetate in that solution that's causing that equilibrium to shift to the left and ultimately lowering the H plus concentration. And we can see that with our X values. The X value here, which is essentially the H plus concentration, in this case is 0.000012, as opposed to the X value over here, which was 0.0019, right? So 2 zeros higher magnitude, right, on the no common ion present than the common ion present. And again, that's why we see the difference in the pH of the two. Questions? Other questions on that? All right. So when we have this common ion sort of problem and effect, which as we will talk about in this chapter pretty much quickly here, this is really what happens when we deal with buffers. And buffers are common ion situation that happens. When we have a reasonably good concentration or initial concentrations, what we start with in terms of the acid and its salts and what we end with in terms of their concentrations are essentially the same number. So again, if we just kind of come back to this example we just did, our X value that we got here in this case was this 0.0040 zeros and a 1, 2. Now, if we were looking at what the concentration of acetic acid was at equilibrium, and I put that number back into here, I would essentially end up with 0.2 still, right? So if you take on your calculator 0.2 and you minus 0.000012, you will basically end up with basically 0.2, which means the concentration of my acid I started with is essentially the same concentration of my acid at the end. Same thing here, if we take our X value and we put it into here, and we add it to 0.3, we will essentially still end up with 0.3. Again, if you put in your calculator, 0.3 plus 0.000012, you end up with 0.3, which again is the same concentration that we started with. And that again is a direct result of this Le Chatelier's principle, pushing the equilibrium back to the left. Not much is coming off, basically, in this case, right? A very, very small amount of anything is changing. And when you have this type of situation, maybe the good news, I'm not sure yet, but we'll see, is you might not have to actually do an ice table at all. And you could use everybody's favorite equation, which is the Henderson Hasselbalch, David Hasselhoff equation, whatever you want to call it there. And this equation here is the pH is equal to the pKa plus the log of the concentration of the base over the acid. So basically it is the pH is equal to the pKa plus the log of the base over the acid. To calculate the pKa value, you take minus the log of the Ka value. So you take the Ka value, which is the equilibrium constant for the weak acid, take minus the log of it, and you can get that. So you could actually use this equation here, and as we will talk about, this is essentially the common ion equation that you should use, more commonly referred to as if you have a buffer, you could use this situation. And again, we're going to talk about buffers next in this chapter, and buffers are really a common ion situation that occurs. Now, this is a pH version of this equation, and you have a pKa value that goes with it that you can calculate. There's also sort of a, much like we have pH and we also have POH, there is a POH version of this equation. And the POH version of this equation is the pKb plus the log of the acid over the base. It is reverse. And it's the pKb value. And by the way, the pKb value is minus the log of the Kb value. Yeah. So the pKb is basically calculated the same way as you calculate the pKa. Now, why would you want to use this? My answer is I don't know why you would want to use that one, because probably in most cases you're going to be asked for the pH. So why not just use this one and you get the pH at the end and you're good to go? Some people like to use it in a basic situation and get the POH, and then you could get the pH obviously by subtracting 14 like we did previously. But in my opinion, I probably wouldn't use it all that much. I'd probably roll with the Henderson-Hasselbalch equation with the pH, because again, I would say 99.9% of the time you're going to be asked what is the pH of the solution. So why reinvent the wheel? Now, what would happen in a basic condition is if you have a base or a basic sort of condition, you may have only the Kb of that value available to you, which obviously in the case of the Henderson-Hasselbalch equation, you would need the pKa value. So you actually have one of two ways you could get to the pKa value if you only have the Kb. You could obviously still use Ka times Kb equals Kw like we did before, and obviously convert the Kb into a Ka and then take minus the log of it and get the pKa value. So that's one way. An easier way might be this relationship, which is if you take the pKa value and you add it to the pKb value, guess what? It equals 14. Yeah. So if you have the Kb value and you maybe want the pKa value, you could calculate the pKb and just subtract 14 and you'll have the pKa value. So that's a helpful relationship right there. So the Henderson-Hasselbalch equation, you definitely can use in any situation, acidic, basic, neutral, it doesn't really matter. But again, if you use that, remember that is not the pH, the POH, and things are reversed. So you want to be really careful in case you try to choose to use that one. You also want to make sure that you get the base over the acid when you're using the Henderson-Hasselbalch equation, right? And our acid typically should have like one more hydrogen than the base, right? Because it could donate it. So sometimes that's a hard thing to figure out. So again, my opinion, I would roll with the Henderson Hasselbalch in all situations. This is also a helpful sort of relationship, again, in case you need to get yourself to a pKa value. So how's that work? Let's just say we took the example we just did, which was we got 0.2 molar acetic acid. And frankly, we had 0.3 molar sodium acetate. And again, we have a Ka value of 1.8 times 10 to the minus 5. Now, clearly, if you could recognize that these two things are related to each other, they're related through the 1H plus difference, right? It's a Bronsted-Lowry difference. Again, if you can't see that, just think about this as those two things, the sodium ion and the acetate ion. And now you could hopefully see that this and this is definitely related to each other by 1H plus. And if you can see that, that is the relationship that you need for the Henderson-Hasselbalch equation. And you could go right into the Henderson-Hasselbalch equation plus the log of the base over the acid. We could calculate our pKa value minus the log of the Ka minus the log of 1.8 times 10 to the minus 5 as a 4.74 pKa value. Putting into our formula here, pH is our pKa plus the log. Well, this is acetic acid, which would make me think strongly that that is the acid in this situation. And this would be its conjugate base, right? Again, the acid has one more hydrogen than the base, yeah, so it's able to donate it. So we would want to go in this case our 0.3 up on top, which is our base, and our 0.2 on the bottom. And if we do that, we should end up with the exact same thing we had previously, which is 4.92 in terms of our pH. No ice table needed in this case. But what it did show us previously was if you want to do an ice table, you can. Yeah. So the ice table still works in all situations. But in this situation, you can use this. First off, any questions on that? Should you use this in every situation? The answer is no. And that is a problem people have. Error number 3 is I learned this equation. I'm just going to use it every time I have two numbers because two numbers is what I need. So I'm just going to put it in every time I have two numbers. So you cannot use this in every situation. You really can only use it in a specific situation, which is really a common ion situation, more commonly referred to as you have a buffer happening, basically. So if you have a buffer, you could use this. If you do not have a buffer, you should leave it on the side so you don't get it wrong. Yes, and you should not use it. So that's a super common error people make is they try to use this like everywhere. They got like two numbers. And the other important thing is obviously you can't use these if these things are not related to each other. And that's a good way maybe to remember that so you don't end up in that trap. Is like even though you still have two numbers at the end, are those two things related to each other? If they're not, you probably should definitely not be using this thing. Any questions on that? So let's take a look at one here. What is the pH of a solution containing 0.3 molar formic acid with 0.52 molar potassium formate? I tell you what, why don't you finish that one up and we'll start with that one next time since we're at the end here.